just fails to work. Okay, no, it's not that. Okay, where was I? So we have x equals v x hat. We have a v x hat equals f, and then we use another matrix which is not necessarily the projection of another one, so we just use v star from the left. So, and what we say with this by orthogonality means that v star v equals identity matrix. So if yeah, so that's the case, and this is Petrov-Galerkin, and our goal is in fact to make this projected system at least, well, symmetric or positive definite. So symmetric and positive. If we manage to do so, then we have all the nice properties of the CG method, and this is also a motivation how these formulas are obtained from the original normal equations. So if we take just a star a in this formula, so what will happen if we have so we have a star a here, then we will have the same v from the left and from the right, and then we can say that w could be just a times v. One example. But it will not be bi-orthogonal, so it's a little bit of tricking. Should be done, but still. Okay, so that's the idea of biconjugate gradients. And the formulas then. So what we are doing, so we basically have similar formulas for constructing such subspaces. We only have the scalar products of conjugate direction and biconjugate direction, and we want this to be not zero. So in some sense, a good way would be that this guy is just a times p, so pj equals a times p. Then we update the solution, then we update the residual. We also have conjugate residual, and we update, so how many vectors we have? We have x, we have two residuals, 3 already, and 2 conjugate directions. So 1, 2, 6, right? 6 vectors. No, it could not be 6 because it should be what? Solution, 2 residuals, 3 and 2 more, 5 vectors. This is also so-called two-sided Lanczos process. So you simultaneously generate the subspace for A, where here it says A transpose, again, just to write A transpose in the case of real matrices and A star in the case of Hermitian matrices. Okay? So even a simple example shows that the solution error, the error oscillates, because this is a projection method. We are not minimizing anything. And there is no garage, there is a quantity that decays monotonically. Therefore, it oscillates. And we have a certain imperative method that converges non-monotonically to the solution. And the ideas, so basically, the idea was that if we have, and this is actually a very general idea, which can be applied to other types of methods. So we have an iterative method that shows non-monotonic oscillatory convergence. What can be done? as well, especially here we are solving linear system. So what you can do is certain averaging or smoothing in order to detect the trend out of this. And this can be done in many ways. So one way is just, okay, if you have a new approximation to the solution, you don't look at it as a new approximation, but you only look at it as a direction for where you go, or maybe the difference between the next iterate and the previous iterate is a direction. And then you have this two-dimensional subspace, the current approximation in the direction, and you can minimize the residual in this two-dimensional subspace. So you do that, you minimize, so on top of the BCG step, you do, for example, just one steepest descent step. And then basically, this is basically the idea of the stabilized method. And then, well, you get a much better convergence, basically much more. So still the convergence is sort of oscillatory, but the oscillations are much less. And BCG stop is the method that is typically used for when you have large matrices and you can store a lot of vectors. So BCG stop is typically the method of choice. The funny fact, which is typically not mentioned anywhere, what happens if you apply BCG stop to a symmetric positive definite matrix? So in each step of BCG stop, you do two multiplications by matrices. One multiplication by A and one multiplication by A transpose. So in the symmetric positive definite case, multiplication by A and multiplication by A transpose is the same. So you do basically two matrix by vector product per each iteration. The funny fact is that the number of iterations required just by the standard implementation of BCG stop is twice less than the number of iterations required by CG. So in symmetric positive definite case, BCG stop produces the same, absolutely the same convergence as the CG method. So if you are completely lazy, you can use the same code for the symmetric case and for non-symmetric case. But okay, doesn't make much sense, but it is not worse. However, there is a common belief that it should be worse. It's not worse, it's the same actually. We haven't seen the proof, probably it's quite obvious. We just look at the formulas and think. There is a very good book by professor from the Netherlands who died recently about alternative. So we are covering this in one lecture and a half. So there is a whole book on iterative graph methods. So we can compare stabilized and not stabilized versions. Again, this is a 300 times 300 matrix. Again, this is a Laplacian. So the BCG stop is obviously better. And so still not monotonic in the relative residual error is because it's not exactly steep as descent, it's a certain smoothing. Yeah, but this area where BCG decides that it should not converge, the stabilized version goes back. And this is a general idea. So if you there is a good paper by the guy whose last name is Wax about smoothing iterative methods for non-symmetric systems, but actually this smoothing idea can be applied to any iterative method that has this oscillatory convergence. So I'm not so sure that such kind of ideas can be applied to non-linear iterations. I hope so. So, okay, there are various contours, but smoothing idea. Because here, if you do a linear smoothing, it's very easy to find the coefficients. So in terms of line search, it's very easy to find the good parameters for line search. Although in non-linear case, it's not always easy. Okay? And finally, before the first part and before the break, okay. So just a short note about very useful thing. Well, it's not, I would say, directly linear algebra. It's a non-linear thing, but it's so nice and so useful, and I think it's important to put it here. So the idea of GMRS is that you collect the basis from the previous steps, and you reuse this information to construct a better approximation to the solution. So if you consider a nonlinear system of equations written in a fixed point form, so we are solving linear system x equals phi of x, and we are solving it using fixed point iteration, xk plus 1 equals phi of xk. So, and actually a funny thing, so nonlinear CG method is younger than the linear CG method. So the nonlinear CG method was born from the linear method. But the GMRS is younger than the method that for the linear case reduces to GMRS. So this one is much older. That's quite funny. Because people often use fixed point iteration. For example, Richardson iteration is fixed point, but they use fixed point iteration in many places, for example, in quantum chemistry. But in robotics, if you do so-called points at registration, you also do fixed point. Almost everywhere you do for solving nonlinear problems, you do fixed point iterations. And the convergence of the fixed point can be very slow. And the key idea is how to speed up the convergence of a fixed point iteration without doing anything. And again, for Anderson, acceleration is ideal tool for lazy people because you do not have to do, oops, what happened? The form was just went wrong. Typesetting math 33%. Okay, maybe we'll have to wait. Something like okay. It's a very difficult math word. Who can read Latin without? Anyone? Yeah, by the way, so we explicitly mentioned that in the problem sets we need expect to have logic, but there were smart people who downloaded the zip file with photos of their notes, which made the eyes of some of our TAs bleeding. There were others, more smart people who wrote a nice text on a web iPad or whatever and put it as a pictures into the. That was better, but formally, like when I have a daughter in the second grade, and when we solve math problems, if they do not put it in the right order, they have just minus. They get minus points for that. Right? If there is, yeah, like the Russians заоформление, you know. So that's what we'll do. So please, if we ask for something and you do not do that, please do not be disappointed that it doesn't work. I don't know what happens to why. Yeah, let's make a